Argon is the 18th element in the periodic table, with the atomic number 18. It belongs to the noble gas group, which is situated in group 18 of the periodic table. Chemically inert, colorless, odorless, and tasteless, argon constitutes about 0.93% of the Earth's atmosphere by volume, making it the third most abundant gas after nitrogen and oxygen. Despite its abundance, argon went undiscovered until 1894, when scientists Lord Rayleigh and Sir William Ramsay isolated it while attempting to understand discrepancies in the density of atmospheric nitrogen. The name argon is derived from the Greek word argos, meaning inactive or lazy, a reference to its remarkable lack of chemical reactivity. Argon is a noble gas, which means its outermost electron shell is completely filled. This full valence shell makes argon highly stable and unreactive under most conditions. Unlike metals, which form compounds readily, or even nonmetals like oxygen and chlorine that engage in a wide range of chemical reactions, argon remains chemically aloof. This property makes it extremely valuable in applications where chemical reactivity must be avoided, especially in environments where oxidation or other reactions would otherwise pose a problem. One of the most significant uses of argon is as a shielding gas in welding and other high-temperature industrial processes. In metal fabrication, argon provides an inert atmosphere around the weld area, preventing the oxidation of metal surfaces and ensuring strong, clean welds. This is particularly important in the welding of reactive metals such as aluminum, titanium, and stainless steel. The gas's density, greater than that of air, allows it to effectively blanket the work area, displacing oxygen and moisture. In the electronics industry, argon is used to create an inert atmosphere for the manufacturing of semiconductors, flat panel displays, and other electronic components. Its non-reactive nature helps maintain the purity of materials and prevents contamination during delicate processes such as plasma etching and sputtering. Additionally, argon is employed in the production of silicon wafers and in the annealing of semiconductors, where even trace levels of reactive gases could damage the final product. Argon also plays an important role in the lighting industry. It is commonly used in incandescent and fluorescent light bulbs to prevent the oxidation of the filament. In gas discharge lamps, such as those used in signage, argon glows with a pale lavender or bluish light when an electric current passes through it. Sometimes it is combined with other gases like neon or mercury vapor to produce a range of colors. Argon's use in lighting extends to laser technology as well. Argon ion lasers, which emit bright blue and green light, are used in scientific research, medical treatments, and even artistic light shows. In the field of cryogenics, argon is valued for its relatively low boiling point of negative 185.8 degrees Celsius. It is used as a cryogenic coolant in situations where extremely low temperatures are needed, but where reactivity or flammability would pose a risk if other gases like hydrogen or oxygen were used. Liquid argon is also used in scientific experiments requiring ultra-clean, inert conditions, such as in particle physics detectors, including neutrino observatories and dark matter experiments. Its scintillation properties, ability to emit light when hit by particles, make it ideal for detecting faint particle interactions. While argon is generally considered biologically inert, it can have physiological effects under certain conditions. For example, in high-pressure environments such as deep-sea diving, argon is not used as a breathing gas because of its narcotic effect at depth. Inhaling argon at high partial pressures can lead to symptoms similar to nitrogen narcosis. For this reason, other inert gases such as helium are preferred for deep-diving gas mixtures. Argon's isotopes also have scientific and practical applications. The most abundant naturally occurring isotope is argon-40, which forms primarily through the radioactive decay of potassium-40. This process forms the basis for a dating technique known as argon-argon 40R39R. Dating, widely used in geology and archaeology to determine the age of volcanic rocks and ash layers. The accuracy and range of this technique make it invaluable for studying Earth's geologic history and the timing of prehistoric events. Although argon is often used as a pure gas, it is also frequently mixed with other gases to tailor its performance for specific applications. For instance, in welding, argon may be combined with small amounts of carbon dioxide, helium, hydrogen, or oxygen to adjust arc characteristics, improve penetration, or influence bead appearance. These mixtures allow for flexibility in working with different metals and thicknesses, helping operators achieve the best balance of quality and productivity. From an environmental standpoint, Argon poses minimal risks. It is non-toxic, non-flammable, and does not contribute to greenhouse gas emissions or ozone depletion. Its inert nature means it does not participate in chemical reactions in the atmosphere, and it is not classified as a pollutant. Industrial argon is typically obtained as a byproduct during the fractional distillation of liquid air, a process that also separates nitrogen and oxygen. This makes its extraction efficient and cost-effective, particularly in facilities already producing oxygen and nitrogen for medical or industrial use. Economically, argon is relatively affordable due to its natural abundance and ease of extraction, though its price can vary depending on purity level and region. High-purity argon, required for electronics or scientific use, undergoes additional purification steps and can be significantly more expensive than lower-grade versions used for welding or insulation. Argon also finds use in niche and emerging applications. In the food industry, it can be used to displace oxygen in packaging, thereby extending shelf life and preserving product quality. In winemaking, argon is sometimes sprayed into wine bottles to prevent oxidation during bottling or storage. In the medical field, research is ongoing into argon's potential neuroprotective effects and its use in cryosurgery, particularly for destroying cancerous tissues. One interesting application of argon is in window insulation. Double or triple pane windows can be filled with argon gas between the glass layers. Because argon is denser than air and has lower thermal conductivity, it reduces heat transfer and improves the insulating performance of the window, contributing to energy efficiency in buildings. In summary, argon is an essential element in modern industry and science. Its chemical inertness, abundance, and versatility make it an ideal choice for a wide range of applications, from welding and electronics to lighting, cryogenics, and scientific research. As industries continue to seek safer, cleaner, and more reliable processes, the role of argon is likely to expand even further. While it may be inactive in the strict chemical sense, argon remains highly active in shaping technological and scientific advancement.